In section 6.1, we're discussing the law of sines. Now you'll see the objectives of this section. Of course, it is to use the law of sines, but most importantly here, you need to understand that the law of sines is going to apply to oblique triangles. Now we'll define oblique in a minute to be any triangle that's not a right triangle. So it gives us some mathematics to be able to deal with all these triangles that are not right, because in fact, the majority of triangles that we work with are not right triangles. The Pythagorean theorem does not apply. We'll be able to use the law of sines to solve, if possible, the triangle or triangles in the ambiguous case. The ambiguous case is going to be when we're only given one angle. And in those cases, the reason we call it ambiguous is because there could be no solution, there could be one solution, and there could be two solutions. So we have to think about it before we just proceed head fast into the problem. And then find the area of oblique triangles. That's going to be really easy. Anytime you know two sides and the angle between them, it's just going to be 1/2 times the product of each side times the sine of that angle. We'll look at that in our formulas. And then solve applied problems using the law of sines. Now, first of all, this is what I was talking about on the previous page, an oblique triangle. An oblique triangle is just a triangle that doesn't contain any right angles. It could have, one obtuse angle. It could have all acute angles like I've drawn up here. But no matter what, it's just a triangle that has no angle that's a 90-degree angle. Other than that, we can be pretty satisfied that, it's just an ordinary triangle, nothing special about it. Now, one thing that I did want you to make note about it is I said the relationships among the sides and the angles of right triangles defined by trigonometric functions are not valid for oblique triangles. So please don't give me that SOHCAHTOA stuff or Pythagorean theorem. You cannot say the sine of the angle theta is equal to the opposite side divided by the hypotenuse, because there isn't a hypotenuse. But what you can rationalize just by common sense here is that the larger the angle is, the larger the side opposite that angle is. So if angle A is larger than angle B, then side A would be larger than side B. And we'll talk about that in one of our, as we go throughout our problems. Now, law of sines. If angle A, B, and C are measures of angles in a triangle, and side A, B, and C are the lengths of sides, and we always measure the sides opposite the angles. You might notice how I labeled this in the last problem. Angle A, the side opposite that angle is side A. Angle B, the side opposite that is side B. Angle C, the side opposite, side C. And we always use lowercase to denote sides, capital letters to denote angles. Now, we're just saying that the ratio of the sides over the sine of the angles is proportional for any of the angles A, B, and C, and sides A, B, and C in the triangle. Now, something else is that the reciprocal of this identity is also valid. So you can say, well, the sine of angle A divided by A is equal to the sine of angle B over B is equal to the sine of angle C over C. It's not just in this direction. If it's equal this way, then the reciprocals are also equal. And the way I always use the law of sines, if I'm solving for a side, then I make sure the sides are in the numerator. If I'm solving for an angle, then I make sure that the sine of A, the sine of B, and the sine of C are in the numerator. It really helps out and makes the problems a little quicker. Now, whenever we solve for oblique triangles, we're going to be able to solve any of the cases in which we'll know a ratio of a side and the angle opposite that side. Looking at our first example here, if we have the side and then two angle scenario. Anytime you have two angles, that's the easiest case, because of course it's very easy to find the third angle, because we know the sum of all angles within any triangle is 180 degrees. So let's say we have our triangle here given, and that we know the measure of A is 64 degrees. We know the measure of angle C is 82 degrees. And we know the length of side C is 14 centimeters. So everything's labeled on your triangle. Now, we're supposed to be able to solve for everything else in the triangle. When it says solve the triangle, it's wanting you to find every other term in the triangle. Now, the way that I did that in the homework, let me show you that just a second here. The way that I did that in the homework, before I worked any problem, I went ahead and did an answer block for solve the triangle. It means you need to know every side and every angle. So as we go through, I wanted to make sure I answered everything in the question. So I would start off by doing all of this and then show you where it comes from as I go throughout the problems. And again, as always, please note, I put the corresponding number to my math lab beside the number in the homework. Now, back to our problem. So we're looking at this one, and I can say, well, all right, we have our three angles sum up to 180 degrees. So that just means that angle B has to be 180 minus the other two angles, 64 and minus 82. That ended up giving me a 34-degree angle for angle B. Now, once I know angle B, it's going to be pretty easy to find everything else that I need in this problem. I need to find side B and I need to find side A. So it looks like I tried to solve for side A here first. I'm using the law of sines where I can say A divided by the sine of A is equal to C over the sine of C. Of course, I'm using the equivalency C over the sine of C because I know the length of side C and I know angle C. So I can say, well, all right, now if A over sine A is equal to C over sine C, then it's as simple as multiplying by the sine A on both sides. And you can get A is equal to C sine A divided by the sine of C. That's what I've done right here. Now within this problem, we just plug it in and we say, well, C is 14. The sine of A is going to be the sine of 64. We're dividing that by the sine of 82. And in all of the homework, whether it's on my math lab or in the book, it's wanting you to round every side to a tenth of a decimal place and every angle to the nearest angle. So in this case, we get 12.7 centimeters. Now, for the next value, we're still trying to find the length of side B. And in this problem, we've already found angle B to be 34. So I just brought that over to the next page. We know angle B is 34. We've already found side B. Sorry, we've already found side A. We're trying to find side B on this slide. Well, I can find side B on this slide because I can say, well, B over the sine of B is equal to C over the sine of C. Therefore, side B is equal to C sine B divided by sine C. That's what I have right here. And then I can say, well, all right, once again, that's just going to be 14 times the sine of B, which we know is the sine of 34 degrees, divided by the sine of C, which is still the sine of 82. When you figure that out, you'll get your 7.9 centimeters. Now, note in this problem, the larger the angle, the larger the side is opposite. So the 82-degree angle had a 14 centimeter side opposite it. The 64-degree angle had a side opposite it of 12.7. The 34-degree angle only had a side opposite it of 7.9. So you can see the larger the angle, the larger the side is opposite it. You can use that to kind of double check just to make sure you don't make a silly calculator error or something like that. Now, the angle side angle case, you still have two angles. So it's still a very, I don't want to say easy case, but it's the easier case of the law of sines. Because we can still say, well, since you know two angles, it's very quick and easy to find the third angle. In this case, we know that angle A was 40, angle C was 22.5. We had to solve for this angle B up here, and just by the appearance of it, we can tell it looks to be an obtuse angle greater than 90 degrees. When you solve out, you would just say 180 minus 40 minus 22.5, and you'll get that angle B is 117.5 degrees. Now, I can then say, well, all right, I'm supposed to find side C, and it would be side A up here. I decided to attack side A first in this problem. I know that A over the sine of A is equal to B over the sine of B. Well, I know that B is 12, I know that the angle opposite is 117.5. So I can say, well, I can solve for A then by just saying A is going to equal B. And in order to get side A all by itself, I would multiply by the sine of A on both sides. So I'll get A is equal to B times the sine of A divided by the sine of B. And then that's just going to give me 12 times the sine of this angle, which was our 40 degrees given in the problem up here. 12 sine 40 over the sine of 117. And I see that the side A up here is only 8.7 centimeters. So if your base down here is 12, and then this side is going to be 8.7. Now our remaining side, which clearly looks like our smallest side, the side opposite angle C, is called side C. Found that here on my next page. I said, well, again, I know C over the sine of C should equal B over the sine of B. Thus, C is going to equal B times the sine of C over the sine of B. Notice that's what I've done. I said C is equal to B sine C over sine A. So now I can say, well, B was my 12. I'm dividing that by the sine of angle B, which we had defined, sine of 117.5. And then we can say, well, that 12 is multiplied by the sine of angle C, which was given in our problem to be 22.5. Whenever you multiply this out, again, your calculator to the nearest tenth of a decimal place should tell you it's 5.2 centimeters. Now, the case that I think might be a little bit more challenging in this section, the side-side angle case. Whenever we're using the side-side angle case, the first thing we're going to have to do is find the second angle. And that second angle, it could be an acute angle, or it could be an obtuse angle, or there might not even be a possible angle. It might be impossible from the way that the problem is given. Let me reference that in my homework just a second. I'd like to show you where I did that. So the problems in the homework that start with this ambiguous case are number 17 out of the book, and it's going to be number 9 on my lab. So you're going to start off, and they're only going to give you one angle. The angle that they gave me was A. In this case, they told me it was 40 degrees. Now, I had to find the rest of them. Well, the first thing I had to do was try to find angle B. I had side A and side B. So I said, well, the sine of angle B divided by the side opposite it, 15, should equal the sine of 40 divided by the side opposite it, 20. So then that told me that the sine of B should equal 15 times the sine of 40 divided by 20. But now, whenever I did that, I said, well, then B is going to equal the inverse sine of that answer. And I went to my calculator, and my calculator told me to the nearest degree, well, that's going to be 29 degrees. But I need you to remember, the problem with trying to do inverse sine on your calculator is it's only ever going to give you an answer between negative 90 degrees and 90 degrees. It's not capable of giving you an obtuse answer. So you have to be capable of understanding when it tells you 29 degrees, there's another value that has that exact same value over here at 151 degrees. So please notice here, just if you did this, you could say, well, I could say the sine of 29 degrees and the sine of 151 degrees, they're guaranteed to be identical, the exact same value. The y value in the unit circle goes up about 0.484 there. So we can say, well, that could occur at 29 degrees or 151 degrees. Now, in this problem, why did I say that that is not possible? And of course, I got the 151 by just saying 180 minus that angle. But the reason I said it's not possible is we already had an existing angle in this problem that we already knew, 40. So you said, well, 151 plus 40 would exceed the amount of angles you have for a triangle of 180. That's why I said not possible. On all of the one solution case problems, you get this answer, and then you say, well, test the second one. And if it adds up to be more than 180 with the angle that you already have, that second answer, not possible. And I go out and finish the problem as a one solution case. You'll see the next one here, same thing. When I found my angle, it told me that, well, the angle B could be 52 degrees. So I had to think, well, 52 degrees, it could also be an angle 128 degrees in quadrant 2. But then when I compared that with the angle I already had, 63 degrees, it would tell me that that's going to be greater than 180. That second angle is not possible. Same thing for the next one after that. Then finally, once I got to 23, or probably about the time you get to number 12 on my lab, you'll get to the case where it's not one solution. And number 23 or number 12 on my lab, when I tried that one, the first thing I did, tried to find angle B given the information I had. But notice, whenever I did the sine of B and said that, well, it's going to equal your 40 times the sine of 30 divided by 10 from your base formula here as you try to solve for the sine of B, I automatically knew, well, the sine of 30, that's just 1/2. So my numerator is going to be 20. My denominator is 10. This is saying the sine of B is 2. You automatically should know that is impossible. The sine function can only ever go between -1 and 1. So for what angle is the sine function 2? No angle in existence. So you just say that's the no solution case. So the no solution case is when it's going to be setting your sine function to a value larger than it could ever be. Now, of course, if you just try to do that on the calculator, you'd have been saying, well, it's the inverse sine of 2, and it's going to tell you error domain, no solution. Now, the ambiguous case where we have 2 solutions is like the next problem. And again, this is how I tried to show it. So you go in, you try to solve for one angle. Again, here I was given angle A. I had to solve for angle B. I was given that information initially. So I said, well, the sine of B over 18 should equal the sine of 16, or sorry, the sine of 60 over 16. So then I said, well, then that's going to give me that the sine of B is equal to 18 times the sine of 60 over 16. When I went to my calculator and said, well, angle B is going to equal the inverse sine of that function. And whenever you're entering that into your calculator, you can literally just go inverse sine. Now, please make sure you're in degree mode for these problems. We'll go inverse sine, and then I just typed it as 18 sine 60. Close out the trig function, divided by 16, close out the inverse trig function. And when I did this, I got the, they wanted us to round to the nearest degree, so 77 degrees. But I had to think, okay, my calculator is only capable of giving me this answer. Could there be another answer? I said, well, the other answer, if there is one, would be 180 minus 77, which would be 103 degrees. So please notice now, whether you take the sine of 77 or the sine of 103, obviously it's the exact same y value. So you say, well, all right, they should be both solutions. Can the second one be a solution? All I'd have to do is say, well, add it to whatever your existing angle is, which would be 60 degrees. And you'd say, oh, 103 plus 60, that's 163. You still have 17 degrees left over for angle C. You have the 2 solution case. Now, remember, when it's the 1 solution case, like some of the early problems, the angle that you have added to your existing angle is going to exceed 180. And you say, oh, the second solution is not possible. When it's possible, you'll add it to the existing angle you know, and you still have room left over. And so then you have to literally work 2 separate problems. You'll work the problem as if the first angle was the solution, get all of that answer done, and then you'll work the problem again, whereas the second angle was your solution for B. And you'll see here, I just did first solution like this. My second solution, I labeled everything A sub 2, B sub 2, C sub 2. I did it similarly in the PowerPoint slide. Wanted to just point that out as you're going through your homework there, so you can see for help should you need it. Now, let's go back to the PowerPoint slide. I'll pick up here. So the ambiguous case. First of all, I'll look at the no solution case here. That no solution case, you saw it in my homework. It's where you're going to set the sine of B equal to a number larger than 1. It's just not possible. So you'd say in a case like this, whenever you try to solve for b, the sign of b is going to be a number larger than 1, and you just say there is no triangle possible. You can't have a side that large for that angle. Now, and again, that's the only thing you'll have to do. If you forget that part, your calculator will handle it, because when you try to do b is equal to the inverse sine of the function, it's going to tell you error domain. So the no solution case, pretty straightforward. It's the two solution case that's usually pretty confusing. So again, you're only going to be given one angle and two sides. So then you can say, well, all right, since I know side B, I should be able to find angle B. All right, so I can say, well, A over the sine of A is equal to B over the sine of B. If you cross multiply here, you can get A sine B is equal to B sine A. And then you're trying to solve for sine B. So you can say, well, sine B is equal to B sine A divided by A. And then I can say, all right, this should allow me to solve for the sine of B. The sine of B is equal to side B, 16, times the sine of A, which is the sine of 35, divided by side A, which is 12. So I'm getting sine of B is 0.7648. So it's telling me the y component on the unit circle is 0.7648. I know there's an answer in quadrant 1 and quadrant 2 where that could be true. Now, when I go to my calculator and say, well, the inverse sine of 0.7648, it's going to tell me to the nearest degree that's, well, it's 50 degrees. But now I need to understand, yes, there's another angle. And all I need to do is say, well, it's 180 minus 50. 180 minus 50 is going to give me 130. Now, could my other angle be 130? You bet it can. How do I know it can? Well, we both should know it can, because your other angle in your triangle is 35. So you can say, well, since 130 plus 35 does not exceed 180, both 50 and 130 will be solutions. So that's what I tried to show here, is that my first triangle is going to be when angle B is 50 degrees. My second triangle is going to be when B is 130 degrees. And both of those are valid because they both yield sums less than 180. Now I know in triangle 1, my remaining angle, angle C, would be 180 minus 85. It's going to be an obtuse angle of 95. Whereas in triangle 2, angle C is going to be a tiny angle of only 15 degrees. Both of these are possible triangles where every single fact that's given in the problem is true, though. So now I just have to work out the two separate problems. For the first problem, I find all of my angles, just like I was talking about. I need to find angle C in triangle 1, need to find angle C in triangle 2. And then once I have that information, I can find side C. I can say, well, B over the sine of angle B in triangle 1 should equal side C in triangle 1 over the sine of angle C in triangle 1. So when I solve out for that, if I'm trying to solve for C1, I can just say, well, clearly from this, you can just multiply by the sine of C1 on both sides and get side C1 is going to equal B times the sine of C1 over the sine of B1. And then we plug that information in, and you'll get 16 times the sine of 95 over the sine of 50. And in this case, that reduces down to 20.8. We knew that side C1 would be the longest because its angle opposite it was the largest in this triangle. So it just makes sense that, yeah, it's going to be larger than 12 or 16. And obviously it was. Now, on the other hand, if it's the second scenario, we know side C is going to be our smallest angle, well, smallest angle and smallest side. In order to solve for it, you would just say side C2 in our second triangle is going to equal B times the sine of angle C2 divided by the sine of angle B2. And we get 16, and remember angle B in triangle 2 is 130, multiply by the sine of 16, the sine of C2 in the numerator. When you put that into your calculator, to the nearest tenth of a decimal, you're going to get 5.4 centimeters, clearly smaller than either of these two, which we should have expected it to be. And both of these two are valid solutions. And so you would just finish out listing all of the information from the problem. I would strongly encourage you to do like I do in my homework, especially on tests. In fact, on a test, I'll probably just put a little answer block at the beginning with angle A, B, C, side A, B, C, just to make sure you're answering everything in the question. Now, easy part of this, area of an oblique triangle. Now, we know the area of any triangle is 1/2 base times height. So if you looked at this, you just say, well, why can't I just say the area is the base 1/2 the base C times the height H? Well, what if you don't know the height H? Then all I would have to do is say, well, I could draw a perpendicular to the base of that and make a right triangle within this triangle. And then I can say, if I did that, then my laws of Pythagorean triangles do work, and I could use my SOHCAHTOA. And I could say, well, H, wouldn't that just be the side opposite angle B? And in that triangle, the hypotenuse would be A. So you could say, well, yeah, that's valid. You could also say over here that the sine of A should equal H over B. Now, because of all of that, we can go in and say the area of the triangle, you can say it's 1/2 BC sine A. So if you know the sides B and C, you only need to know the angle of the angle between those sides to find the measure of the triangle. So it's 1/2 BC sine A. Or what if you know sides A and B, sides A here and B here? Well, then your area of the triangle would be 1/2 AB times the sine of the angle between them. And lastly, well, what if you know sides A and C? Well, again, the area of your triangle is just going to be 1/2 AC times the sine of the angle between them. That's always going to work. Now, your problems are going to be very straightforward. You'll be given two sides of a triangle and the angle between them, and just say, well, then I just plug it straight into my formula. My formula is going to tell me it's 1/2 8 times 12 times the sine of 135. And when you plug that in, that's 1/2 times 12 times 8. We know the square root of 135 is square root of 2 over 2. But your book's always going to have you round to the nearest meter anyway, so you don't need to keep it precise. And we can just say approximately 34 square meters in that case. Now, this is like the first of the application problems. In the book, it was number 47. On your MyLab assignment, it's number 21. So looking at it, it says you have two lookout fire stations are 13 miles apart. So that's my fire station A, fire station B, 13 miles apart. Now with, it says both stations spot a fire. So your fire is going to be up here at point C. And it says the bearing of the fire from station A is 35 degrees east of north. So I had to say, well, this fire, which is up here at point C, it's located 35 degrees east of north. So I can label this right here as 35, which also means that I know that this angle right here inside the triangle has to be 90 minus 35. That's going to be a 55-degree angle right inside there. You can see I labeled angle A as 55. Now, it also says that the fire is located 49 degrees west of north from station B. So 49 degrees west of north. Well, I know this angle here is 49. That's 49 degrees west of north. So then your remaining angle down here, angle B inside the triangle, would be 90 minus 49. 90 minus 49 is going to give me 41. So this angle inside the triangle would be 41. Now, we're supposed to find out how far to the nearest tenth of a mile is the fire from station B. Okay, so Here's the fire, here's station B. So I'm trying to find side A right here because it's opposite angle A. In order to do that, I do need to find the measure of angle C. Well, that's easy though, since I know the measure of B and the measure of A here. I figured those out by subtracting these angles from 90. I can easily say, well, then the sum of the angles inside the triangle, which is 55 plus 41 plus C, has to be 180. I add these two together, I get 96. So C is equal to 180 minus 96. Angle C up here is an 84-degree angle. Now, once I know that angle C is that 84-degree angle up there, then I can say, well, I have enough information to find this side right here. I know side C, and I know the sine of angle C. I know angle A. I can easily find the side opposite A. So I would say A over the sine of A should equal C over the sine of C. Now, here I cross multiply, but I would almost rather you just say, well, if you're trying to solve for A, just multiply by the sine of A on both sides. And then you'll get A is equal to C sine A over the sine C. That's what I have right here. Now, plugging in your information, you can say, well, you have 13 times the sine of 55. You're going to be dividing that by the sine of 84. And then we would get approximately 10.707, which your book is always going to want rounded to the nearest tenth, and same thing with my lab. So you'll get approximately 10.7 miles is the distance the fire is from station B. Of course, we could do the same thing to find the distance from station A, and it would be a very similar process. Okay, guys, that'll do it for the law of sines. Please let me know if you have any questions. I'll be glad to help.